I'm just covering the cause live.
Okay. Settle down, settle down. Alright. So first of all, what is first of all? First of all is, I'm not going to give you another homework assignment before the end of the semester, but I am going to give you your take-home final next Tuesday. And you'll have until the day of our final. Yes?
Are you going to be extended office hours next week?
Am I having extended office hours next week? Yeah, I'll have some extended office hours, some extended office hours next week, later in the week.
Like specifically probably like Friday.
Specifically, probably actually not Friday. Sadly, Friday is, so it's your day off to study, and therefore all of the departments do their big end of the year meeting. So I have a retreat on Friday, which is really code for a 6-hour meeting. But I will, I mean, I might be able to do some later Friday, it just depends, and then also the following Monday of finals week, I'll do some office hours. So I'll give you, and I might even be here on the weekend, I don't know, I'll set something up for sort of help later in the week.
Is this going to be similar to the GR final where it's do it yourself, but you can sort of collaborate? How are we working?
I don't remember.
If it's in office hours, you're collaborating.
Yeah. So you are allowed to collaborate within the context of my office hours. And the reason for that is because when you're in my office hours, you're not just copying down what somebody else has written. If you come to my office hours, you're going to be at the board just like everybody else working stuff out. Anyway, all right. So if you did the pre-lecture reading, then you're aware that I have decided to go ahead and start with QCD. This will probably likely occupy us for the next 2 lectures. And so since you guys didn't seem particularly fond of the idea of having a final exam period lecture, what we'll probably do is talk about QCD, and then in our last lecture next Thursday we'll talk about renormalization, and then we'll just kind of skip the weak interactions. So we won't do any actual calculation with the weak interactions. And truthfully, if you kind of know how QCD works, the weak interactions is just the same, but more of a pain in the butt because of various things. But anyway, I feel like if you can get your head wrapped around QCD, you could pick up what you need to do for the weak interactions, given the final rules, which are on the sheet that I printed out for you. So there. Okay. So we're gonna
And based on last lecture with calculations, we only do one diagram. Is there a rough order of magnitude? Like if you add more diagrams, you get so much more accuracy? Is there kind of a rough rule, or is it just?
Well, we're going to talk a little bit about that today, about what diagrams to keep, what diagrams to throw away, what's important, what's not. But generally, I was just picking problems for you where, especially in the situations where you had to calculate the spin average m squared, if you only have one diagram, then the square is simple because it's one term squared. The minute you have 2 diagrams, then you've got to expand that thing out and you get cross terms. And then you can imagine if you have 3 and 4 diagrams, you square it, you get a lot more. So I was just trying to pick a scenario, so a process where in leading order there was only one diagram. There are certainly processes where at leading order there's more than one diagram. And then you can always go to higher order. And you've already probably seen this, that if you go to like 4th order, there's usually a lot more than one diagram.
Well, yeah, how much more accuracy does going up an extra order give you?
Well, there's a couple of things that impact that, and we'll talk about that today, but largely you take well, actually, I think I will address that at some level in what I'm about to write on the board. Perfect. Okay, so, the dangling thing. I should probably not pull it, that would be bad. So we're going to talk a little bit about hierarchy of interactivities. Because there are some things which are somewhat counterintuitive with regards to interactivity. So first of all, let's remind ourselves very quickly what in the standard model feels what, okay? So the neutrinos in the standard model only experience the weak interactions. the charged leptons Kaylin, what's a lepton? All right. Kellen, sorry. Kaylin, I knew that was Kaylin. I hope he's not asking me. My name's Kellen. I knew that sounded wrong when it came off my tongue. I was like, there's no Kaylin in this class. Kellen, what's a lepton?
Something that can feel anything but the strong force.
That's a good way to put it. I like that. Yes, as I wrote it. So, for examples of leptons are?
Neon, tau, lepton.
Okay, good. So, you can look at this in one of two ways. You can either say that the weak interactions are sort of the most pervasive interaction. Everything experiences the weak interaction. So they're kind of like it's the overlord of the interactions. Electromagnetism is, it plays a role in more particles, but QCD is sort of the least present in terms of what matter particles they can interact with. Another way to think about it is like the neutrinos, they're sort of the most sterile of the standard model matter particles. They only interact via the weak interactions. Charged leptons, they're a little bit dirtier, and then quarks, they're dirty little whores. They do it any way they can. And but what's important, and maybe surprising to you if you haven't actually explored diagrams of higher order, is that these conclusions are only relevant for direct interactions. So what do I mean by that? Well, to give you an idea, let's take, for example, a process wherein we have an electron come in, an electron go out, a muon come in, and a muon go out. And then the idea is, given that process, what various contributions would we use to fill in the bubble, to complete the picture, and hence give us different contributions to the amplitude M. And we're all aware that there is an electromagnetic process where you exchange a photon, okay? There's a direct electromagnetic interaction between the electron and the muon because they're charged leptons. Similarly, it turns out that in any diagram you can draw where you have a photon, you can also draw the exact same diagram, but with a neutral weak boson, Z0. Z0 plays a role very analogous to the photon. Two important differences being that the Z0 is massive and the photon is massless. That's going to be that's kind of a very important impact in just a minute. And then the other thing is that where you can replace a photon with a Z boson anytime it appears, you cannot always replace a Z boson with a photon. Can anybody give me a case where you could not replace a Z boson with a photon? Neutrinos. Yeah, so Z bosons actually interact with neutrinos. So I could actually draw this picture with two neutrinos interacting through the exchange of a Z boson. But since they're not charged, they don't exchange photons. Okay? And you might say, all right, good. We got that. We expected that. But now I want you to consider a higher order diagram, which remember it's a part of the answer. It might be something we neglect if we're just making an approximation of using the first few lowest order terms. But if you truly want the answer for what the amplitude M is, you have to take into account all of the diagrams. And so for instance, our process could very well involve a photon, but that photon might, in a moment of panic, burp out two quarks in a quark-anti-quark pair. This is an electromagnetic interaction because quarks are charged. So that's just a normal QED vertex. But once I have quarks in the picture, what can quarks do with each other? They can exchange gluons. So strangely, even though we started with a process entirely in terms of charged leptons, QCD has snuck into the story. Okay. So two takeaways from this. One, when you get to higher order, things get really complicated really fast. Okay? And second, when we say that these particles only experience certain forces, we're really only referring to the direct interaction. Okay? All right, so now we're going to talk a little bit about QCD. Well, actually, let me say another couple of things regarding these. The three interactions actually each have a coupling constant. Okay, this is the quantity that enters into the Lagrangian when you see the interaction as a product of three fields. It's part of what came into the story when we formed the gauge covariant derivative, making the symmetries local. That coupling constant determines the sort of fundamental strength of that interaction. Okay. Now, what might be surprising to you and seems somewhat counterintuitive is that the strong interaction has the largest coupling. The weak interaction has the next largest coupling. And the electromagnetic interaction actually has the weakest coupling. And then if you really wanted to just continue the story, the gravitational interaction has the smallest coupling by a long shot. Okay, but we tend not to keep this in the standard model. By the way, if you did want to try and work quantum gravity into this picture, everything feels quantum gravity, everything can exchange gravitons because everything carries energy, and energy is the source of the gravitational field. And by energy, I also include mass. So what's interesting about this relationship, well, it's a couple of things. First of all, why do we call this the weak interaction? If it's stronger than this, well, it's weaker than strong, so this kind of is intuitive. But why isn't this the weak interaction and this the not so weak interaction? Strong, medium, weak. Okay. Secondly, why is it that in our day-to-day life, this seems to be the interaction that we deal with most often? Okay. Why the electromagnetic interaction? Why don't we do tabletop experiments with the strong interaction or the weak interaction? Well, the answers to that are actually interesting and surprisingly different. We'll talk in a few minutes about why the strong interaction is not as prevalent in sort of tabletop scenarios as compared to the electromagnetic interaction. But in answering why the weak interaction is not as relevant as the electromagnetic interaction, this stems from exactly the type of process that I just described. So if we have an electron-electron and muon-muon, and a photon exchanging between them, we can always replace this with the corresponding weak interaction diagram, where this is the Z naught. If you calculated the amplitude m for each of these diagrams, you know what this is going to look like. It's going to have two vertex factors. Those vertex factors are going to have, for the electromagnetic case, IgE times the gamma mu squared. And it turns out the vertex factors here are similarly going to be proportional to the square of, we might as well just call it the weak coupling, and I'm just going to come in here and cheat and call this the electromagnetic coupling. So with that in mind, since alpha W is bigger than alpha E, one would assume that just based on the vertex factors, this diagram would be bigger in its contribution to M than this one. But what's the other part of the story? The propagator. Because both of these diagrams have an internal particle, and computing M requires putting in a propagator factor. And what's very important about the propagator factor, if you look on the little sheet that I gave you, if we look at the propagators for spin 1 particles, because both the photon and the Z boson are spin 1 particles, then we notice that in this case, the propagator, as we've already seen in quantum electrodynamics, is just going to come in with a factor of Ig mu nu over Q squared. However, since the Z naught boson is massive, we get a more complicated propagator. But what's important to note is the denominator. The denominator brings in a factor of the mass of the Z boson. So if I actually took this whole thing as sort of the effective electromagnetic interaction strength and compare it to this whole thing as a measure of the effective weak interaction strength, now this quantity is smaller than this quantity by virtue of the fact that the particle that's being exchanged is so huge. Now, don't get me wrong, if you actually looked at a process where the momentum exchanged in the process was on the order of the mass of the Z boson, then this contribution can actually become comparable to this, okay? And that's a story that we'll actually see play out in more detail when we look at renormalization. Two hands up.
Why does subtracting mass in the denominator lead to a smaller value?
Because this value right here is always going to be much smaller than this, so the denominator is going to be negative anyway.
So it's a greater magnitude on the negative.
Yeah.
Okay.
Can we take all of what we're learning this week and all that and just throw in a different G if we're doing it in a different space? Is that, or are there other?
If we're doing it in a different space?
Yeah, we're not doing it in constant space. Let's say we are talking about the particle physics near. Because it seems like we keep putting G in there and say, oh, we're just using eta. Is it simple that we can put like
Yeah, sorry,
a
this
Schwarzschild
is just
metric
eta.
in there? Black hole and then work in that area?
Yeah, it is almost. So sorry for this diversion, but in GR we learned that there's a minimal coupling prescription for how to do physics in curved space. And there's two very important things that you have to do. One is everywhere you see the Minkowski metric, you replace it with the curved space metric. But the second thing is everywhere you have a derivative, you have to replace it with the covariant derivative, including the Christoffel connections. And those don't appear anywhere in here. So the metric in flat space is still non-zero, it's just got a special form. But in flat space in rectangular coordinates, the Christoffel connections are zero, so you don't know where they would appear. It'd be hard to go back and stick them in. That's how you would do it. Okay. All right, so the weak interactions, we call the weak interactions, all right, not because the coupling is weak, but because the gauge bosons are so massive. So when we compute the amplitude for a process like this diagram actually has a much larger contribution than the corresponding weak process. So when you're evaluating the importance of diagrams, and this is the question David was asking, to first order, it's probably not the right way to say it, but as a first rule of thumb, you count the number of vertices. The smallest number of vertices typically wins. Okay? But you also have to take into account that just because two diagrams have the same number of vertices doesn't guarantee that they're actually going to have the same level of contribution, because you have to take into account modifications like the mass of the mediators. So it gets to be a really tricky process. Now, one thing to point out is we know that in truth, these are a part of the same electroweak interaction. And so if you actually start doing experiments at an energy scale above the masses of the Z and the W bosons, you're actually probing the unified electroweak theory. And in that case, these two numbers are actually the same. They have to be, because there's only one interaction, the electroweak interaction. The fact that these have different values is again a consequence of renormalization, which we'll talk about next week. Okay, so the other issue is, why are the strong interactions weak? And of course, or why are these strong interactions not so important? And you can clearly see that this, or the ghost of it, is not going to provide an explanation for why the strong interactions are not so weak. And why would that be the case, Henry?
Well, the strong interaction side, sorry.
So the argument I just made for why the weak interactions are weak compared to the electromagnetic, why is that argument not going to work for the strong interactions?
Because the electrons don't feel strong interaction.
Well, if you just took quarks and you looked at quarks, which feel a strong interaction. Phone friend?
Yeah.
Robin?
Because gluons are massless.
Because gluons are massless, so they don't get this mass suppression that you get from the weak bosons. Okay. All right. So to move on to quarks, we of course now have several. If I take two quarks and I let them scatter, say an up quark and a down quark. Actually, that's the process. Up quark comes in, up quark goes out. Maybe a down quark comes in, down quark goes out. And I want to calculate that scattering amplitude. Then we know that this has contributions from all three forces. Quarks, they're the dirty cores, they fill everything. Okay, so they can exchange photons because quarks are charged under the U1 of electromagnetism. They feel the weak interaction. So I can replace that with a Z0 boson. But then they're quarks. And so they can also interact directly via the exchange of gluons. Of course, at higher orders, you would have expected all the interactions anyway, but you have direct interactions. Yes?
Could we even have a diagram? Because you can't have some of the quarks.
Okay, well, we're going to talk about how we actually think about this in a minute, all right? So you can't have single quarks, but one way of thinking about this is how do I explain if I have a bound state of an up and a down quark, the mutual interactions between those two, what's keeping them bound? Okay, so this is kind of a funny scattering process because the two particles you start with are not free, they're bound, but they're bound and then they're bound. So it's not like you're breaking apart a bound system or forming a bound system. You start and you end with a bound system. All right. So today we're going to talk about this. This is QCD. We're probably not going to talk so much about this, and we might not get to it by the end of the semester. But we should already know how to do this, right? This is just quantum electrodynamics. That's what we spent the last couple of lectures going over. And you might ask, well, what changes when you do quantum electrodynamics for quarks? Fortunately, pretty much nothing. The only difference is that for quarks, we have fractional electromagnetic charges. So when you write down the vertex factors for a quark diagram, instead of just putting in the fundamental electric charge, which is all we ever use for leptons, because they always have integer charge, whenever we put in vertex factors, we just have to throw in the appropriate fraction associated with the charge of the particular quarks involved. Okay? And this was actually a very poor example. Now that I think about it, oh no, it's fine. Yeah, it's fine. Okay, so that's it. We just did quark QCD. I mean quark QED. Any questions? You're literally just doing everything we've done for electrons and muons and tauons. It's just the vertex factors get some little fractions in there because the quarks have fractional charges.
Is that, at least based on what you just gave us, there are more vertex possibilities than QCD or QED?
So the primitive vertex is still the same.
Yeah.
It's a charged particle coming in and a photon coming out, and this is always the same particle.
Yes. But we also have those other two. Looks like it's the photons and gluon interactions, maybe?
Oh, I'm talking about just QED.
Oh, okay.
QED,
Okay.
not QCD, or the weak interactions.
I see.
Okay? So if I'm only thinking about photons, okay, so the electromagnetic interaction, then it's exactly the story that we played out over the last couple of lectures.
Thank you.
Okay? So now let's talk about QCD. Just as the story of QED took the ABC theory and added a whole layer of complexity, because now we had spin matrices and spinners and little spinners, and we had to form spinner sandwiches because order mattered. QCD is going to take QED and add a whole other layer on top of it. Because unfortunately now, as we're already aware, in QCD, it's not a quark field, but a vector of 3 color quark fields. And the transformations, instead of being numbers, are 3x3 matrices. So we're going to have all of the love of QED plus some more matrix love. Okay, so let's do it. Yeah! Matrix love. All right, so let's start by reminding ourselves of the deliciously simple Lagrangian for QCD. Oh, and I don't have. Oh, damn. Well, actually, I guess I can do it this way. So we've got the usual Dirac Lagrangian for the quark fields, psi. And I'm sure I'm going to get this wrong because I've got all this new notation and terrible like that. Okay. So remember, this capital D mu is secretly hiding the interactions between the quarks and the gluon fields. This d mu is actually little d mu minus I times the gauge field, where there's 8 of them. But in addition, we get a whole nother level of fun, because when we go to write down the gauge field kinetic term, where the gauge fields are also now indexed by letter A because there's 8 of them. We get not just this simple looking field strength like we got for electromagnetism, but we get these other nice factors. And there's a lot of love in these 3 additional terms, okay? These 3 additional terms are effectively responsible for the interactions between the gauge bosons themselves, because the A's are the gluons. And this is a product of gluons. This is a product of gluons. This is a product of gluons, okay? So we can already anticipate that in QCD we're going to have additional vertices. Clearly we're going to have gluons interacting with quarks, but we're also going to have gluons interacting with gluons in both triplets and in quartic pairs. All right, so that's our QCD Lagrangian. Let's think about the right way to. Well, we'll just do it this way. Okay, so here we go. So quarks in QCD. So we'll recall the color. So we have 3 colors. Remember, QCD is weird because we've got weird numbers that crop up. We've got 3 and then we've got 8. We have 3 color charges, red, green, and blue. They're not 3 values of a single color charge. They are 3 distinct types of charges. It's almost like if you had 3 different electric charges, and you can have different values of each of them. Okay. So we have 3 color charges interacting with 8 gluons. Again, in QED we would only have 1 charge and 1 boson, gauge boson. Here we have 3 charges, 8 gluons. And there's a couple of things that are useful to note in terms of organizing how we're going to work with QCD. First of all, as we've already alluded, quark states, or quarks always appear in either quark anti-quark bound states or three quark bound states. And those can be three quarks or three anti-quarks. You do not mix up quarks and anti-quarks in a three quark bound state. Okay. These are called the mesons, these are called the hadron, or sorry, these are the mesons, these are the baryons. These two quarks don't have to be the same. It could be an up and a down quark. Likewise, these three quarks don't have to be the same. Okay. Altogether, these are called hadrons. Okay. Today, we're going to spend most of our time focusing on the mesons. We might next time talk a little bit about the baryons. They just have an extra layer of complication because there's three instead of two. But then the other thing to remember is that gluons come in color-anticolor combinations. In fact, this is the way that we actually built up the strong interaction from SU3 invariants. We found that the gluons are the generators, or associated with the generators of SU3, and they basically take a color state and turn it into another color state. So you can think of the gluons as kind of being bicolored as well. So both quarks and gluons are bicolored. Or sorry, both mesons and gluons are bicolored. However, they're sort of opposite in what we observe or what exists. Okay? So mesons are overall colorless. Okay, they carry no net color. What I mean by that is if I take a typical meson, a Q and a Q bar, if this is a red quark, this is automatically an anti-red quark. Again, they don't have to be the same flavor of quark. This could be an up and a down, but this would, if this was a red up, this would have to be an anti-red down. Okay? The gluons, on the other hand, are always colorful. Okay? Well, you might say, well, why are gluons colorful? There's two answers for that, but let me actually sort of catalog the set of working states that we're going to talk in terms of, and then I'll come back to the question of why can't we have a colorless gluon? Yeah.
Is there some sort of kind of quantum field when you look at a meson that if you can detect one of the quarks inside of it, it determines what the other one is? It's like there's kind of a probability of it being red, and then you'll automatically make the one the anti-red?
Yeah, I mean, they're entangled in that sense, for sure. I mean, they have to form a color singlet. So this is exactly perfectly analogous to an angular momentum singlet, where you know if one's spin up, then you automatically know the other one's spin down. Perfectly analogous. Okay, so it turns out that if we're going to take three colors and we're going to always think of color anti-color states, then we might as well go ahead and write down sort of a useful basis to work in. So let's start. We'll start with what we call the octet of colorful states. The word octet being, or implying that we have 8 of them. And I'll just list them out here. And unfortunately, it's not perhaps the simplest combinations that you might think of. But I'll tell you why we use these in particular in just a moment. And then we have a color singlet state, or a colorless singlet state, which we could call 9. And it is 1 over root 3 red bar plus blue bar plus green bar. Okay. Now, if you look at this for a minute, so we tend to think of these as colorful, but actually the way that we should think about these things is that this set of 8 states are transformed into each other via SU3 transformations. Okay? So if I take one of these, say state 4, and I act on it with a non-trivial SU3 transformation. Of course, the identity is part of SU3, and if you act with the identity, you just get back the same thing you started with. But if I take a non-trivial SU3 transformation, then it's going to take this state and turn it into a possible linear combination of the other states. However, this singlet is invariant under SU3. Okay. Which you can almost kind of guess. This is sort of like the length of a color vector. And SU3 is just rotating in color space. So it's leaving this guy fixed, but it's rotating all these into each other.
How is state 3 colorful? Because we have a color that
Right. So this is so I should be a little bit careful in my language. I should distinguish between colorful and non-trivial under SU3. So it is colorless. You're exactly right. So this is colorless, and in fact, this guy is colorless. But what's more important is whether they're trivial or not under SU3. Because if SU3 has a non-trivial effect on them, then they are going to experience the interaction with the particular generator associated with that transformation.
Did you say anti-green? Do you mean negative unit green charge? Is that what?
Yeah, you can think of it that way.
So when you wrote quarks always come in mesons or baryons, the Q bar, that's just saying it's the anti-color?
Yeah,
Right.
It's not necessarily the same quark flavor. So this
Right.
could be Q and Q prime. Likewise, this could be 3 different quarks.
But
So when we're talking about the strong interactions, we don't actually care so much about the flavor.
Right, it's color.
We're just thinking about color. So when you go to strong interactions, don't even think about up quarks, down quarks. Just think about red quarks, green quarks, and blue quarks, because that's what's going to matter. Okay. Other questions? All right. Now, when I say that gluons are colorful, what I actually have in mind is that the gluons correspond to combinations which transform things non-trivially. Okay. We don't have a gluon in this singlet colorless combination, and there's 2 ways to think of that. One is, if there existed a gluon which was colorless, it would actually have properties identical to the photon. And if it had properties identical to the photon, it would actually be able to replace the photon in any diagram. Since that gluon is massless, it would play as prevalent a role in nature as the photon. But clearly the photon plays a more important role than any of the gluons, at least in terms of direct interactions. So experimentally we know that this gluon can't exist, because if it did, we would basically have a second version of the photon. The other is that if this existed, the symmetry group underlying the strong interactions would actually be U3 and not SU3. Okay, but we've seen the structure of SU3 pop up in other areas. So it's exactly taking all possible combinations and then throwing out this colorless one that actually gets us from U3 down to the SU3 of the standard model, leaving us with the 8 non-trivial gluons. Okay, now I'm going to keep this stuff around because these particular combinations are going to be useful in an argument that we're going to make about why quarks appear in bound states. So, all right, it is time to write down the Feynman rules. And you already have these to some degree on the sheet in front of you, but the way that I'm going to do it is maybe going to be a little bit clearer. For purposes of comparison, what's so funny, Jacob?
Mark's whispering secrets in my ear.
Mark, we're whispering secrets in Jacob's ear. You guys are making me nervous, like my pants are juice or something. All right. Oh my gosh. Yeah, okay, I've got some room for this. Did you guys write this down?
Totally.
I squeezed myself into this narrow channel where I'm not going to be able to fit in what I need to write, but I'll try. As some of you have noted, I do at times demonstrate my prowess for tiny handwriting. So here we go. So and since I'm going to be writing so much, I probably won't read it out. I'm kidding. So we have I'm going to do this for the ABC theory, just to kind of go back and remind ourselves where we started. I'm going to do it for QED, and then I'm going to do it for QCD. And this will give us a nice way of just kind of understanding the layers of complexity that are getting added on in each case. So for the external state labels, in the ABC theory, Marcus is going to be happy to tell us what labels we used for the external states in a diagram. In the ABC theory.
Oh, ABC.
What did we use? When we wrote down M in the ABC theory, what did we use for external state labels? Nothing. They're spin zero particles, and the external state labels are just specifying the spin state. If it's spin zero, there's nothing to specify, so there's none. Okay? In QED, we used U bar, V bar for external matter. So if our diagram had matter particles coming in or going out, we use these spinners U bar and V bar. But of course, we could also have photons coming in and out. And so we didn't actually do very many we didn't do any calculations in the homework with external photons. But if, for example, you want to talk about Compton scattering, the scattering of a photon off of a charged particle, then your diagram would have an external photon, and you would write down photon polarization factor in calculating M. In QCD, it's going to get more complicated. In QCD, the quarks, those are the relevant particles, have spin. So we're going to have to specify their spin state. But they also have color. So we have to specify their color state. Fortunately, we can just decompose those two labels. We can specify the spin state with a spinner U, and U bar and V and V bar, and then the color state with a color vector that we'll just call C. And then, of course, we have, for dual spinners, we utilize the Hermitian conjugate of the color vector, and then similarly VC and V bar C dagger.
Do you not have to switch the order when you do the Hermitian?
Do I need to switch the order of these two?
Yeah.
It's not important because they're non-trivial in two different spaces.
Okay.
This is in color space, and this is in spinner space. So I can flip them around. Again, this is the love of QCD. You're going to be working in actually four different spaces. You're going to work in space-time, so that's where your mu, nu indices are going to be. You're going to work in spin space, That's where the gamma matrices are non-trivial and the U's and the V's are non-trivial. You're going to work in color space. That's a three-dimensional Hilbert space with red, blue, and green basis vectors. And then you're going to work in the what did I call it? The gluon space, which is an 8-dimensional state space spanned by the octet basis states of color and anticolor. So you're 4 different spaces that we're going to be talking about in QCD, and we're going to have objects which are trivial in one, non-trivial in the other, trivial in all of them, non-trivial in a couple of them. So it's going to get crazy.
Is it the
Get a little cray-cray.
same?
Yeah.
Is it the same U and V from QED?
Yeah, it's exactly the same labels that we used for QED for the U's and the V's, and you use them in exactly the same places.
I mean,
if it's
like
a
exactly the same, like.
expression too, yeah, identical. And we apply them in the same way. If we have an outgoing particle, that's a U bar, and if we have an incoming particle, that's a U, and so forth and so on. So that part of the story you just get to just carry over from QED. The C's are going to be the new part, all right? If we were crazy enough to actually consider processes with external gluons, then again, since gluons are spin-1 massless particles, just like the photon, they're going to need a polarization vector, but the gluons carry bicolor. So they're going to need an additional degree of freedom, not a C. C is just color. C is red, blue, green. The gluons are bicolored. Okay? There's 1, 2, 3, 4, 5, 6, 7, 8 possible gluon states. So we got to give them a different label. So that'll be A alpha. And then if we have a outgoing A alpha star node. For now, don't worry so much about labeling external gluons. We're not often going to think about that, but these same factors are going to come into internal gluon propagators.
So a gluon can be states 1 through 8, but not 9, right?
Right.
So,
Quark-bound states can only be 9 and not any of the 8.
okay, and I know this was similar to a previous question, but why is, for example, 3 and 8? Why are those allowed? Those look colorless to me. But 9 is not allowed.
For a gluon?
Right.
Okay. So let's go back to what does a gluon do?
I mean, it mediates
It mediates.
the strong.
It mediates the strong interaction. So a gluon, if we have a quark coming in and a quark going out, the gluon that is mediating the interaction that forms this vertex, in order for it to actually do something, it has to transform this in some way. It has to be non-trivial. Okay? And what I'm trying to argue here is these look colorless. Where's the other one? That one. But if I do an SU3 transformation on them, they change. So something being colorless does not necessarily mean it's invariant under SU3. Okay, another way to think of this is if you take the components of the vector and you square them and add them, that is invariant. But if I was silly enough to do this, it's not invariant under rotations. It's still built out of the same things, the squares of the components, but it's not invariant. So we need the gluons to be non-invariant under SU3 because they actually have to affect a change. That's where the interactions come from.
Okay.
I agree. You know, off the cuff, it seems a little confusing, but yeah.
Can you find
I just pick favorites.
can you find a freely propagating label?
I don't know the answer to that question, actually. Well, gluons actually have a very interesting property because they're self-interacting. You can actually have gluon-anti-gluon pairs. You can get bound states of gluons called glue balls. There's a lot of really interesting exotic physics that you get out of gluons. Generally speaking, we don't just have free gluons roaming through the universe, but the strong interaction is a funny thing because remember, it's the one that's going to behave backwards with regards to how its coupling changes with energy scale. It's going to be very weak at high energies and very strong at low energies, which is exactly the opposite of electromagnetism. So generally speaking, whatever you expect from electromagnetism, expect the opposite from gluons. So if you see a lot of photons, you don't see a lot of gluons because they behave oppositely. Yes?
So you said that singlet state acts like a photon, like it's almost like...
If it existed, it would act like a photon. Yes.
So why can't we, it might be naive of me to say, if we include that state and call it the photon, is that a unification of QED and QCD then?
That would ostensibly be a unification of QED and QCD, with the exception of the fact that we would then have a hard time explaining why that photon doesn't interact with leptons. If the only thing in the story were quarks, yeah, it would provide like a unification. Okay. All right. Okay, so fundamentals. Here we go. I got my external state labels. And then, of course, if we have a diagram and that diagram has internal particles, virtual particles that begin and end within the diagram, then we need propagators. So we now have propagators. For the ABC theory, where life was nice and easy, we just had one type of propagator because all of our particles were massive and they were spin zero. For QED, if we were fortunate enough to have an internal virtual matter particle, then we would include a propagator of that form, as you saw in problem 5 of the homework. Typically, though, we have internal photons, and for internal photons, we just throw down a propagator factor of that form. Okay? Again, this is a review. This is QED. You've been working with this already. What's it going to look like in QCD? Well, if we have gluons, if we have quarks internal, then we get a propagator factor much like, actually identical, to the propagator factor associated with matter. This, you might anticipate, the propagator is doing nothing but telling us about sort of the kinetics of having a particle exist and move. So relations between energy and momentum and mass, etc. Okay? You know, if you have an electron or a quark, you can have a quark in a QED diagram that's internal. And the kinematics of that quark existing and moving through space-time is not really any different if you consider QCD. Okay? However, of course, if we have gluons, then we would expect a slightly more sophisticated gluon propagator. Where we have to remember now that the gluons are connecting vertices, and so their color state has to actually match up with the color of the quarks that they're mediating the interaction between. We'll see how this actually comes into play when we start looking at some diagrams. Yes?
Why are we still using eta if gluons live in like gluon space?
Okay, so this eta is a representative of the fact that the mediator is spin one particle in space-time. That hasn't changed.
Oh,
okay. Okay, the photon is spin one, massless spin one, the gluons are massless spin one. So you'll notice it's still got the minus I eta mu over q squared. The difference is that where the photon has no charge, no extra thing to specify, the gluons have charge. They have color charge, and so we have to specify that in their propagator. Okay. Okay, that's a good question. All right, last but not least.
Quick question on the last one.
No! No more questions! No, just kidding. What?
That alpha beta, so that's not space-time. Is that like
I'm going to talk about all these things in a minute. I just want to get them on the board, and then I'm going to come back and I'm going to pick on different things and say, this is what this is, and this is what that is. Okay, so let me get everything up here. So our fundamental vertex in the ABC theory was just ABC meeting at a point, and we wrote down a factor of minus IG. We know for QED, the fundamental vertex is a photon emanating from some matter line, and whenever we encountered it, we would write down a factor of minus IgE gamma mu. In QCD, we have a more complicated Lagrangian. First of all, in this term here, we have an interaction that looks just like QED. This is just going to be, if I expand this derivative, it's going to be d mu, and I can't remember the coefficients, but something like that. And so when I sandwich it in between these psi bars and psi's, I'm going to have the gauge field with the matter fields. And so we know we're going to have a vertex in QCD that looks somewhat like the QED vertex, except this time it's a gluon. And the factor that we write down in this case is going to be very similar, with the modification that we use the strong coupling instead of the weak coupling. And by convention, you put in a factor of 1/2. It's still going to require a spin matrix. All of the spinner part of the story persists in QCD. So pretty much anywhere you expect to see a metric or a spin matrix, it's going to show up in QCD as well. But we're now also going to have to take into account the fact that there's this color factor in the story. Okay? But that's not even the end of it, because QCD has more stuff. In particular, in these two terms, I should expect a vertex with 3 gluons. Here I expect a vertex with 4 gluons. Those are going to have more complicated factors. If I write them down, oh my God. Should I? I'm not going to write them down. They're on your sheet. Look at your sheet. Yeah, I'm not going to write this down. So if we turn to QCD, you'll notice the three vertex factor and the 4 vertex factor. Now, something that's interesting in these factors that's a bit different, especially, this 3 vertex factor. If you look at that picture, you'll notice that it has momentum labels on it, whereas all the other vertex factors don't. Can anybody tell me why the momentum labels might be important for that 3 vertex QCD factor, whereas they don't seem to appear anywhere else?
The kinematics are different. You have 2 and it's on now, right?
Because there's derivatives. on
Yes,
there.
good, exactly. If you look at this Lagrangian, one of the gauge fields in this product, you're looking at the derivative of it. Here, it's just straight up a product of 4 fields. Okay? So it turns out that the momentum flow actually becomes an important part in constructing the vertices associated with these 3-point interactions in QCD. Okay. Yeah, Robin.
So does that mean that other momentum vector interactions don't exist because it only has the one where like everything's coming from vertex?
No. So all that's doing is it's labeling the 3 momenta, and then based on that labeling, it's writing down the form of the vertex factor. You can pick different directions for the momentum, but then that changes the form of the vertex factor.
Okay, does it change just like signs or?
Yeah, it just changes signs, just literally flipping signs. But you gotta pick a convention, and then you write down the factor, and then it changes. So does everybody understand what Robin's alluding to? If you look, I'm not going to write some of the board, it's too big. If you look at the 3 vertex factors, you'll notice all the momentum lines go into the vertex. So Robin was asking, does that mean that's the only way that you're allowed to put the momentum in a diagram if you have a 3-point interaction? And the answer is no. You can always turn one of the momenta around, but in the factor to the right, you have to reverse the sign of that momentum. So this is the form of the factor for this assignment of momenta. If you change it, you have to change the factor accordingly. Yeah.
I'm also noticing that the gluons themselves have arrows. Do we need to attach arrows on the photon? It seems like the gluons have at least some sort of...
Okay, so that's a good question. So in a normal QED diagram, we draw something like that, but we never put arrows on the photon. So back in the QED story, what do these arrows help us indicate?
Particle antiparticle.
The difference between a particle and antiparticle. However, the photon is its own antiparticle. Okay. Good? All right, so
Wait, I'm not good. Why don't we do arrows on the gluons like David was asking? I understand for QED with arrows like that.
why don't we do arrows?
Yeah, 'cause-
we do arrows.
Oh, okay.
We do arrows on the Gluon ones.
Okay.
Yeah, they're tiny. They're on there. You'd think
Okay.
Alex wrote this. How
Well,
tiny.
no, I know you were just talking.
Yeah,
about
I'm sorry.
QED.
Yeah, I'm being lazy. I'm being incredibly lazy.
Okay.
I should draw my arrows. Yeah. Okay, much of the stuff that we're going to actually do with QCD is going to rely on this vertex. We're not going to worry so much about the 3-point and the 4-point vertices. But clearly, if you want to look at exotic things like blue balls, bound states of quarks, that's going to become a very important part of the story, all right? And a much more complicated part of the story. Now, you'll notice you'll be able to identify certain factors that come into play when you look at these. Well, actually, let me just, now that I've got this sort of identified, let me get rid of this and go through what some of these things are. So let's talk a little bit about what these various things that are appearing in the QCD ingredients actually correspond to. So first of all, we'll start with color. So we know that there are 3 types of color, red, green, and blue. Now when we write down a process, and I have to put this in, I don't want to write red, green, or blue. I actually want something that I can eventually turn into a number. So what we're going to do is construct a 3-dimensional color Hilbert space and then set up a basis in that Hilbert space with some unit vectors. So why don't we just go ahead and say that we're going to take C1 to be 1, 0, 0, and let that be red. And then similarly, C2, 0, 1, 0, we'll call that green. Actually, I will call it blue. I don't know why I'm changing the order of the colors, but it doesn't matter, it's all convention. 0, 0, 1, and we'll call that green, okay? Now, these are all real, right? Nothing complex there. But when I form an arbitrary color state, I actually make a linear combination of the color basis states, and these coefficients I allow to be complex. So the total color state can be a complex vector. That's why I've got daggers here instead of just transpose. Okay? But now you know what these C and C dagger factors would look like. I would specify I've got, this much red, this much blue, this much green. You write down the linear combination, and that's C. It's a 3-component thing. And then if you instead need C dagger, you flip it, complex conjugate. All right? The A alphas, these are the 8 gluon states. So if you will, we can set up a basis in the 8-dimensional Hilbert space of gluon states. So we might as well just pick a simple basis. Okay. So whenever I have a factor of A that I have to specify in a gluon state, I'm just going to pick one of these, which is really just saying I'm going to put my gluon in one of these states. So this would be the 1, 0, 0, 0, 0, 0, 0, 0. 0, 1, 0, 0, 0, 0. Okay. I'm just turning these letters into something I can actually make numbers out of. That's all I'm doing. All right, and then lastly, the lambda alphas. In QED, remember, or well, I mean, I guess it's in QED, but it's also in QCD as well. Remember we had these funny little things, the gamma matrices? They secretly carried spin indices, but we never really wrote them because we're lazy. You can think of the gamma matrices as sort of linking up two of these spaces. They link up space-time with spin space. They kind of bridge those two different spaces. They're non-trivial in space-time because they carry a vector index, and they're non-trivial in spin space because they carry a spin index. Okay? The lambdas that appear, you can think of in QCD as bridging color space with gluon space. Okay, so analogous to the gamma is kind of linking up two different vector spaces. Here, the lambdas are going to play a similar role where instead we're linking up color space to the gluon space. So secretly, what we should really say is that this is a vector in the gluon space. So a lambda will have 8 possible values for its alpha, but it's going to secretly carry 2 color indices. It's going to be a matrix in color space, but you know I'm never going to rank that. Now, you might say, wait a minute, what the hell? Lambda is a vector in gluon space, and it carries 2 color indices. Okay, that's kind of similar to this, right? But why? Like, why? Why would it do this? Why would there be 8 of them, and why would they have 2 color indices? What are these? They're the generators of SU3. These are the generators of SU3. You looked at these in a homework assignment when we talked about SU3 as a gauge theory. Now, why does that tell me why it has this structure? Well, first of all, how many generators of SU3 are there? 8. There are 8. I need to have something that says which of those 8 I'm dealing with. Why would it have 2 color indices? Well, what does an SU3 transformation do? It takes a color vector and it rotates it. If this is indexed by some color index I, this is a matrix. It's got to have 2 color indices, ij. All right? Okay. Sorry, I got a little excited about that. Okay. When we write the lambdas, though, we're very often just going to leave off the color indices in the same vein that we leave off the ABs. What does that mean? If we're going to leave off the indices, what does that mean?
Order matters.
Order matters, okay? Because we're not going to be using the summation convention. So that means when you put a lambda alpha in somewhere, you got to make sure it goes in the right place so that at the end of the day, everything combines to give you a number, okay? But that's the convention, okay? So that's what we'll do. Now, yeah.
It might notationally like backhanded before the kind of programs that they were writing to be like CERN to run through these kind of things, but they use Einstein summation everywhere.
So there are things that we can say are understood, but the computer does not understand, right? Yeah. So the computer, you have to spell it all out in detail. This is literally what I mean. This is a number, an integer. Okay, so there's one last thing that has appeared. If you look at the vertex factors, which I did not write down because I'm lazy, but if you look at the vertex factors on the sheet, in particular for the 2 gluon-gluon vertex factors, what do you see appearing in there that I have so far not discussed? F. F. What the F? What's F?
What's that?
Well, remember the F's were what were appearing in the Lagrangian. But what are they? Where do they come from? Why are they in the theory? They come from the Lie algebra of SU3. Remember, SU3 is non-abelian. That means if I take 2 generators and I take their commutator, then that commutator can, in general, be written as a linear combination of the other generators. The coefficients in that algebra expression are what we call the structure constants. The fact that QCD is non-abelian is why we got those extra interactions. Turning that around, if I made QCD abelian, the way to do it is to set all the F's to 0, and in that case, all of those gluon-gluon interactions would disappear because they all have an F in them. Okay? So if you're actually brave enough to do a calculation that has those gluon-gluon vertices, and you write down one of those vertex factors, and then you need to go plug in something for F, what are you going to plug in?
0.
No, QCD. Don't abelianize QCD. There are people that do it that don't. What would you plug in for F? You go to that homework assignment, because in that homework assignment I gave you all the F's. I told you what they were. It's just a list of numbers. And you go, okay, I need F1, 3, 6, and you write it down. Okay, I'm not going to write them down for you. You go look it up yourself. Okay. All right, so I think we're probably in a decent place to actually stop. And then next time when we come back, what we're going to do is take this. So I'm going to entertain questions, so don't make too much noise. But when we come in next time, what we're going to do is take this, and we're actually going to start constructing diagrams, and we're going to finally have to be more careful in constructing diagrams. In particular, we've got to pay very close attention to color. So we're going to use the diagrams to actually answer 2 questions. And if you did the pre-lecture reading, you know what those 2 questions are. David? I know you did the pre-lecture reading because you came in with your hippie on.
I read halfway now. I knew we were talking about color. So.
Peter, what are the 2 questions we're going to answer?
What is QCD?
No. That's good though. I like that question. Josiah. Robin. Jesus. Alex.
Peter stole mine.
Claire. Daniel. You got it? You got it?
I'm working on it.
Zach. All right, just tell me. What are the 2 questions?
Why strong interactions between gluons seem weaker than the electromagnetic interactions?
Yes.
Why quarks exist in colorless bound states?
Yes. So the 2 questions, the 2 things that we've already alluded to earlier in the lecture. Why do the strong interactions seem less important than the electromagnetic? And then why do quarks have to exist in these colorless bound states? All right. We're going to use all of these tools in the final diagrams to actually investigate those next time. Are there any outstanding questions about what's on the board? Mark had his hand up at one point, so these could be useful.
So the alpha and stuff for those, I'm guessing eventually you're going to sum on those to kind of weed out specific quark states.
Sure. So in doing the examples that we talk about next time, we're actually going to assign specific color states to things. And then once we've assigned color states, then you have to make the gluon states actually match up with what color states they're mediating the interaction between. So you don't get to freely pick all these indices. They're related to each other in various ways.
Is there any sort of conservation of color that we have to worry about?
Oh, absolutely. Definitely. And it's built into the Lagrangian. Actually, the Lagrangian we wrote down automatically takes into account color conservation, but we'll use that in constructing diagrams for sure. Other questions? You guys scared? You don't mind working in 4 different spaces at once? I know. Hell, I work in 12 spaces. I work in 100 spaces. That's how I roll. Not here. Okay. All right. I'll see you next time. So remember, no homework. And I'm going to be giving you your final exam on Tuesday with a little over a week to do it.